This is AP Calculus BC, and in this video I'm going to talk about section 4.7, which is Newton's method. So Newton's method is one of our applications of derivatives, and what this is really going to do is give us a way that we can approximate the zeros or the roots of a function. So I want to show you what I'm talking about on the calculator first, and then I'll show you how this works. So say, for example, we have the function x cubed plus 3x plus 1, and we graph it. Well, if I graph that function, this is what it looks like. Now, what I'm wanting to do here is I'm wanting to figure out where is this crossing over the x-axis. Okay, that's what I want to know. Now, we can kind of estimate that here, and we can even go on the calculator and we can say, okay, with the calculator, let's have the calculator find the zero of the function. And it'll ask us for boundaries. I'm going to say this looks like it's somewhere between -1 and 0, so left bound and right bound. And then it asks me to guess. Now, make note of the fact that it's asking me to guess. It doesn't really matter if I guess on the calculator as long as I have the interval set, but I'm going to go ahead and guess and say, oh, that looks like it's maybe -0.25. So then the calculator will go through and do whatever it does, and it tells me, okay, here's your zero, about -0.322185. Now, the reality of what's happening here is that there's a really, really simple process going on to figure out what the zeros of the function are. And that process is what I'm going to show you. So let me show you specifically what's happening in the background. So this is a slightly different function, but the same idea. When we perform a Newton's method, remember the first thing that I had to do after I set the interval was it asked me to guess. Well, when I guess, essentially what the calculator is going to do is find that point on the function and then create a tangent line. And it's going to say, okay, with that tangent line, where does that tangent line cross over 0? That's going to be my approximation for the point where the 0 exists. Now, obviously, that's not actually the root or the 0, but I got closer to the point. And now we're going to repeat that process. So we're going to find the point on the function, we're going to find the equation of the tangent line, and we're going to figure out, okay, where does that line cross the x-axis? And again, that's not exactly the 0, but I'm still getting closer. And I can keep repeating this process over and over and over again until I essentially converge onto the solution. Now, the idea behind this is very simple because all we're doing is finding the equation of a tangent line, we're setting the y equal to 0, and we're solving for x. We're just doing that over and over and over again. And we can keep running that process as long as we need to get whatever accuracy we want for the root of the function. And that's what I'm going to show you how to do. So the process for this is very calculator intensive. So the first thing that I would tell you is as you go through this, you're definitely going to want to have a calculator nearby because I'm going to go through a lot of the functions that you have to do on the calculator to perform a Newton's method. The most important part of this is to understand conceptually what's actually happening, but you do have to know what buttons to push and what things to do on the calculator to make the calculator actually perform this operation step by step like we're going to do. So here's how Newton's method works. So you can see here I am starting with the equation of a tangent line. And all I have is essentially a point on my graph that we're calling x1, f of x1. If I find the equation of the tangent line at that point, then all I have to do is solve for the y, and that's going to give me an equation that I can use to then set y equal to 0 and solve for the x-intercept. Okay, so that's what's being done here on this step. So we took this equation, which is just the equation of the tangent line, we set y equal to 0, and we got x. So that gives me my approximated value of where does that tangent line cross the x-axis, which is the approximation of where's the 0 for the function. So notice that on the graph here, they called that x2. So really here, x2 is equal to x1 minus f of x1 minus f prime of x1. And then we can just keep repeating that process. So here I've got x3 is equal to x2 minus f of x2 over f prime of x2. So there's sort of a formula that comes from this. And the formula, though, is just essentially rearranging the equation of the tangent line with 0 plugged in for the y. And so this is the process that we're going to follow. When we do Newton's method, this is called an iterative method, meaning that essentially what we're going to do is we're going to have some process that we're going to keep repeating over and over and over again. And with that process, in this case, it's going to allow us to find the roots of the function. In this class, we're going to have a couple of situations where we're going to talk about iterative methods, and these are actually really good ways that we can do very simple math to approximate solutions to sometimes very, very difficult problems. And there's entire branches of mathematics devoted to these approximation methods, and this is one of the most basic ones that you're going to see. Okay, so let's go through how this actually works. Okay, so again, you kind of see the same thing here, repeating this process. Here's my function I'm trying to find the 0 of. We're going to start with some value that we say, okay, I think the root's somewhere around x1. Obviously, we would choose something closer than this to the point, but you can choose anything as long as you're relatively close to that root. So I choose the point x1. I find the point of tangency. I find the equation of the tangent line. Where does that tangent line cross the x-axis? And then we repeat the process. Find the point on the curve. Find the equation of the tangent line. Where does it cross? And then again, repeat over and over and over again. And eventually what I'm going to see is the point that I'm approximating is going to converge to the value that I'm looking for. And we can get as much accuracy out of our solution as we want, depending on what accuracy we need. And the only thing that would change is how many times do we have to run through, or how many iterations do we have to do of this process. Okay, so I'm going to go through one of these on the calculator with you and show you how this works. So this one says find an approximate solution for x cubed plus 3x plus 1 is equal to 0 until two successive approximations differ by less than 0.0001. So I'm essentially going to be accurate almost out to 4 decimal places. Okay, the reason I say almost is because there can be some rounding involved with these digits out here that I'm not really accounting for, but essentially to 4 decimal places. Okay, so on the calculator, here's what we're going to do. Remember in that formula, we had to have the next x value after our guess is going to be x minus f of x1 divided by f prime at x1. So what I have entered here as my y1, I've plugged in the function, and as my y2, I've plugged in the derivative of that function because that's part of my Newton's method process. So what I'm going to do here, I'm going to look at this graph first, and I'm going to say, okay, where does this look like it's close to? And just to make this easy, I'm going to say, oh, that's pretty close to 0. So on my main screen here, I'm going to tell the calculator to treat 0 as my x. So I hit the 0, I hit the store button, and then I hit x. So 0 is being stored as my x. And now this is where I'm going to do my iterative process. So I'm going to put in my formula. My formula is whatever my x value is minus, and then I'm going to put in a fraction. So I want to do my y1 function because that's the original function. I want to do y1 evaluated at x divided by my derivative, which in our case was y2, and I want to evaluate that at x, whatever that x value is. And then the result of that, we're just going to store that as the new x value. So whatever we chose, that's like my x1. After it runs through this process, it's going to store that as x. That's going to be my x2. So I run through this process, and it gives me approximately negative 1/3. Notice I had a pretty significant change here between my first guess and what just happened. Well, I can repeat this process. So there's 2 ways to do this. One way is I'm going to go up here and grab this. I'm just going to hit enter, and then I can now rerun the calculation. It has stored negative 1/3 as x. So it's going to do this now with negative 1/3 plugged in for x, and it's going to run through the same process. And you can see my value didn't change by a lot this time, but it did change by a little bit. So I need to keep repeating this process until I see that there's a change that's less than 0.0001. Now, what I can also do is I can just repeat the operation that I just performed by just hitting enter again. So if I hit enter again, you can see it reran that calculation, and now I got about negative 0.322185, and I'm going to run it one more time, and you can see that we've actually already converged to the level of accuracy that we want. So on this next iteration, I got negative 0.32218535546, slightly different than this one that we had previously, but the fourth decimal place did not change. Okay, so that's the process. Now on the calculator, it's relatively easy to do. And this is what's going on when you tell the calculator to find the zero of the function. That's essentially what's happening. Okay, so we're going to go through a couple of examples of how this works. Now, it's not so much that this is something that you're going to use a lot. It's more understanding with your calculator, what's the calculator doing in the background? Okay, so that's really what the main purpose of this is, so that the calculator is not doing some magical procedure that we don't understand. The calculator is just shortcutting this for us. It's got a little script written in there. It's got, this cycle that it runs through. It's probably got a loop set up, and it just runs through this loop, and it checks this value that it just found versus the previous value. And it's probably got it programmed out to some level of accuracy. And it says, okay, when we see change no longer occurring out at the 10th decimal place, we'll break out of that loop and then we'll report the result. So that's what the calculator does when we do it on the graph and we go through this whole process of finding the zero. Okay, so just keep that in mind. This is what's going on in the background. That's what we're trying to really understand. Okay, so let's go through a couple more examples here, and you'll see how easy this process is once you get it down. The main thing is you've got to train yourself a little bit with the buttons on the calculator to get really good with that. And once you've got that down, this is a really, really quick, easy process. Okay, so let's go through this example that says approximate the square root of 7 to within 0.000001 by applying Newton's method. Okay, so notice they gave us a hint here. The hint is use x squared minus 7 is equal to 0. Well, okay, I'm going to define my function here to be x squared minus 7. Okay, that means that my derivative would be equal to 2x. Okay, so I don't really know exactly what square root of 7 is, but I have a relative idea of what that is. So what I want you to do when you work these problems out, it's understood you're going to do this on the calculator. But in terms of work you need to show, I want you to show me what you use as your first guess. So I know that square root of 7 is somewhere around 2.5, roughly. And I know the formula that I'm going to use to find the next approximated x. I'm just going to use whatever the previous x was minus my function evaluated at that x divided by f prime at that same x. Okay, so that's the process that we're going to follow. And in this case, when I solve this out, that's going to be my approximation for the square root of 7. Okay, so let's go through and actually do this on the calculator. So on the calculator, what I'm going to do here first is I'm going to define my functions. So I've got to take out the ones I had in earlier. And my function was x squared minus 7. So I'm going to enter that. My derivative was 2x. And we've already approximated where the root is, so I really don't need to look at the graph. Okay, so now we said our first guess was 2.5. So I'm going to take 2.5. I'm going to store that as my x value. And now I just need to go through and apply the Newton's method formula and go through the process. Remember, I'm just doing a linear approximation here. Where does that graph cross 0 based on the equation of the tangent line? So I'm going to re-enter this just one more time. I could go back, since I've already entered this whole expression. I could just go back into the history of the calculator and pull it up, but I want to show you one more time. So remember, I want to do the x that I have minus, and then as a fraction, I'm going to put in the original function, y1, evaluated at that x value, divided by the y2 function, which was the derivative. So if I hit alpha trace, I can shortcut to y2, evaluated at that same x value. And then whatever I get, I want to store that as my new x. Okay, so remember, 2.5 was my x1, and when I run through that process, 2.65 is my x2. And now I can just keep rerunning the process. Just keep hitting enter. You can see that here we've changed out in the second decimal place. This would round to 2.65, but I've changed out here in the second decimal place. And we were trying to get accuracy looking at the sixth decimal place. So I need to run this a few more times. Okay, so you can see now I went from X1, X2, X3, X4. I'm not seeing much of a change here, right? But I did still see out in this sixth decimal place, the number did still change. So I haven't quite gotten the accuracy, or at least not verified the accuracy that I want yet. So I've run through at this point 1, 2, 3 iterations of Newton's method because I've applied the formula 3 times. Now when I run it the 4th time, you can see that the value here doesn't change. So that's just basically ensuring for me, okay, now I can say this is my result because I didn't see a change in the value. So this is really sort of a verification step. And so when I'm thinking about how many iterations of Newton's method did I run? Well, I ran 1, 2, 3, got me the answer. And then the 4th iteration is where I just verified that, okay, yes, I do have the actual accuracy that I want. Okay, so it's a pretty simple process. The one thing that can get a little bit confusing is counting your number of iterations. Remember that last step that I run is my verification step. So I don't really say that I ran 4 cycles of, or 4 iterations of Newton's method. I would say I ran 3, and the 4th iteration was my error verification. Okay, so see the number that we got there, 2.645751311. Now what I'm going to do is just show you on the calculator. I'm going to show you the square root of 7, and you can see that it's the exact same value. So using this really, really simple technique, we can solve things like the square root of 7 to whatever accuracy we want. If you wanted accuracy out to the thousandth decimal place, we can get it. If you have a calculator that can perform calculations out that far, you can get whatever accuracy you want. If you want accuracy out to the millionth decimal place, you can get that just by using the equation of a tangent line. So really, really simple ideas allow us sometimes to do really, really powerful things. Okay, so there is one more problem here that I would like for you to try. So first of all, let me just go back here. When you report your result on these, let me show you the way I would like for you to write your answer. So we've got square root of 7 here that we were trying to approximate. So all you have to do, don't say square root of 7 is equal to, because we don't know exactly what it's equal to, but we know it's approximately 2.645751. And I went out to that 6th decimal place because that was really all I was interested in, was out to the 6th decimal place. Okay, so like I said, there's one more here that I want you to try. This one's got a cubic function, and I want you to go through the same process. So this one says they want you to approximate to within 0.00001. So I want you to pause the video, go through this entire thing yourself. It doesn't take that long, and see how many iterations it takes and see what you get for your solution. Okay, so here's the solution that you should have come up with. Notice that there are 3 solutions. So when you graph this one, there's 3 solutions on your graph. You can see that from the graph of the cubic function. So that means that I'm going to have to choose values that are going to lead to each of those individual roots. So this is the part you have to be careful about. So think about on the calculator when you have it find the zeros, it makes you set an interval to find the zeros. This is why it has you set an interval, because if I have too many zeros within my interval, then it doesn't know which one you're trying to calculate. So if you set an interval that only contains 1 zero, it's always going to find that 0 you were looking for. So I started with, the first one was close to 0, and I ran through my Newton's method and got this solution. The next one was somewhere around -2, again, same process. And then the last one was somewhere around 2, and same process again. So it's relatively simple to do, but when you have more than one root, you have to be careful about it. Okay, so as far as the homework goes, make sure when you're working through these problems that you practice writing down the steps that are required to show what you're doing. So yes, most of this is done on the calculator, but somebody who's looking at what you did needs to understand your process. And by writing the function, the derivative, and then showing this is my process and showing what your first guess was, then it's clear, okay, I'm applying this. This is an iterative method, and I'm getting this solution from that. The other thing that I want to mention is if the question says something like, let's say it says, get accuracy out to the third decimal place. If it says something like that, accuracy out to the third decimal place, what you want to be thinking about is having a number out in the fourth decimal place that's less than a 5, right? Because I want to be thinking about how much is that going to change the previous value? Is it going to round up or is it going to round down? So I need that number to change by less than that amount if I'm going to think about rounding to a specific decimal place. So sometimes the questions are worded differently. Sometimes you'll see it written out like this, where they'll give you an actual value that you work off of, or sometimes they'll say accuracy to a certain decimal place. You have to deal with it in a slightly different way. Usually the number of iterations you do won't vary regardless of which way you do it, but there are certain cases where having that extra 0 and the 5 versus the 1 might make a slight difference in the number of iterations that you perform.